Let me ask you something that sounds so simple you might think I am wasting your time. What does it mean to go fast? No, really. You are sitting in a car, driving down the highway at 60 miles per hour. What does that number mean? It means that in 1 hour you cover 60 miles of road. Fine, that is just a ratio. Distance divided by time. A child can understand it. A dog, if it had a speedometer, could understand it. So let me ask the next question. You are in that car going 60, and you throw a baseball forward at 30 miles per hour. How fast is the baseball going? 90, right? 60 plus 30. A 10-year-old gets this. It is so obvious that nobody even bothers to think about it. You just add the speeds together, and right there in that perfectly reasonable, perfectly obvious answer is where the universe has been hiding something from you, because that answer is wrong. Not wrong by a lot. At 60 miles per hour, the error is so unbelievably tiny that no instrument humans have ever built could detect it. But it is wrong, and the reason it is wrong will lead us to the strangest and most beautiful thing physics has ever discovered about the structure of reality. So let us start with this simple addition. You are on a train, a nice fast train moving at 50 miles per hour. You walk toward the front of the train at 3 miles per hour. Someone standing on the platform watches you go by and says, "That person is moving at 53 miles per hour. Makes perfect sense. Galileo figured this out. Newton used it." For 200 years, no one doubted it. This rule, this adding of velocities, works beautifully for baseballs and trains and bullets and everything you encounter in daily life. And it seems to work for one very deep reason. Space is just space, time is just time, and motion is just a matter of covering ground. If I go this fast and I add a little more speed on top, I just go faster. Simple. But then somebody discovered something that made the whole thing fall apart. Not a philosopher, not a mathematician sitting in a room thinking, an experimentalist, a guy with equipment. In the 1860s, James Clerk Maxwell sat down and wrote a set of equations describing how electric and magnetic fields behave. 4 equations. And when he combined them, something unexpected popped out. The equations predicted a wave, a ripple in the electromagnetic field that would travel through empty space at a very specific speed. He calculated that speed, and it turned out to be about 186,000 miles per second. That number matched the measured speed of light almost exactly. Maxwell realized light is an electromagnetic wave. That alone was one of the great moments in all of physics. Think about what it means. Electricity, magnetism, light. 3 things that seem totally unrelated, all unified by 4 lines of mathematics. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. They leapfrog each other forward through empty space, and that leapfrogging ripple is what hits your eye and lets you see. The electromagnetic spectrum, from radio waves to gamma rays, is all the same thing, just different frequencies of this ripple. The light you see is a tiny sliver of a much grander phenomenon, and Maxwell found the key to all of it. But there was something else tucked into those equations, something much more unsettling. The speed that came out of Maxwell's equations did not depend on anything. It did not depend on how fast the source of light was moving. It did not depend on how fast you were moving when you observed it. It was just a number, a pure constant of nature, baked into the equations like the ingredients in a recipe, and that made absolutely no sense. Think about why. If I am on that train going 50 miles per hour, and I shine a flashlight forward, shouldn't the light be going at the speed of light plus 50 miles per hour? That is what Galileo's rule says. That is what your intuition says. That is what Newton's physics demands. But Maxwell's equations said, no, the light goes at the speed of light. Period. Not the speed of light plus anything, just the speed of light. 2 sets of laws, both incredibly successful, flat out contradicting each other. Most physicists at the time assumed Maxwell's equations must be missing something. Maybe light needed a medium to travel through like sound needs air. They called this medium the ether. And if the ether existed, then the speed of light in Maxwell's equations was the speed relative to the ether. Problem solved, except someone went and checked. In 1887, Albert Michelson and Edward Morley built one of the most precise instruments in the history of science. It was called an interferometer. The basic idea is you take a beam of light, split it in half with a partially silvered mirror, send the 2 halves in perpendicular directions, bounce them off mirrors, and bring them back together. When the 2 beams recombine, they create an interference pattern, bright and dark bands of light caused by the waves being slightly in or out of step with each other. The brilliance of this setup is its sensitivity. If one beam traveled even a tiny bit faster or slower than the other, the interference pattern would shift, and Michelson's instrument could detect a shift of less than 1/100th of a wavelength of light. That is extraordinarily precise. The idea was straightforward. The Earth moves around the Sun at about 18 miles per second. If there is an ether sitting still in space and the Earth is plowing through it, then light going in the direction of Earth's motion should be a little slower than light going perpendicular to it, just like swimming upstream versus across a river. The Michelson-Morley experiment was designed to detect that difference. The equipment sat on a massive stone slab floating in a pool of mercury so they could rotate it smoothly without vibration. They took measurements at different times of day, different seasons, different orientations. The expected fringe shift was about 4/10ths of a fringe. Easily within their detection capability, they found nothing. No difference at all. The fringe shift was less than 1/100th of what was predicted, essentially zero. Light went at the same speed in every direction, regardless of how the Earth was moving. They repeated the experiment. They improved it. Other people tried it with better equipment over the following decades. Same answer. No ether wind. No difference. The speed of light was the same in every direction. Michelson himself was disappointed. He considered the experiment a failure because it did not find what he was looking for. It took years for the physics community to realize that the negative result was the result. The absence of the ether wind was the discovery. This was a crisis. Real physics was colliding with real physics, and something had to give. For about 18 years, this problem sat there like a splinter in the mind of physics. Hendrik Lorentz, a brilliant Dutchman, proposed that objects moving through the ether physically contracted in the direction of motion, just enough to hide the ether wind from any experiment. Henri Poincaré in France was circling very close to the right answer. George Fitzgerald in Ireland had similar ideas. They were all groping towards something, but none of them were willing to take the radical step. And then, in 1905, a 26-year-old patent clerk in Switzerland looked at the whole situation and did something that takes either extraordinary courage or extraordinary naivety, maybe both. He said, "What if we just believe the experiments? What if the speed of light really is the same for everybody, no matter how fast they are moving? What if that is not a problem to be fixed, but a fact to be accepted? And what if Galileo's simple rule for adding velocities is the thing that has to go?" Here is what made Einstein different from Lorentz and Poincaré, who had most of the mathematical pieces already. They kept trying to save the old picture. They wanted space and time to stay the way Newton said they were, and they invented mechanisms, physical contractions, local time coordinates to explain away the experiments. Einstein said, "Forget the mechanisms. The experiments are telling us something about space and time themselves. Listen to them." His name was Albert Einstein, and the paper he wrote on the electrodynamics of moving bodies, submitted in June of 1905, changed the meaning of space and time forever. Einstein started with two postulates, just two. First, the laws of physics are the same in every reference frame moving at constant velocity. That one is not controversial. Galileo basically said the same thing. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the source or the observer. That second postulate is the bombshell. It sounds innocent, but follow it to its logical conclusion, and the universe rearranges itself. Here is why. Suppose I'm standing by the railroad tracks, and a train goes by at half the speed of light. That is absurdly fast, but just imagine it. On the train, someone turns on a flashlight aimed at the front wall of the car. They see the light go from the flashlight to the wall. Simple. But what do I see standing on the ground? I see the light leave the flashlight, but while the light is traveling, the train is also moving forward. So the light has to travel a longer path to reach that wall, because the wall has moved ahead. It has farther to go. Yet both of us must agree that the light is traveling at the same speed. The person on the train measures the speed of light at 186,000 miles per second. I measure it at 186,000 miles per second. Same number. If the speed is the same, but the distance the light travels is different for the two of us, then something else has to be different too. Think about it. Speed is distance divided by time. If the speed is fixed and the distance is different, the only thing left that can adjust is time. Time itself must be running differently for the two of us. The person on the train, from my perspective, has a clock that is ticking slower than mine, not because the clock is broken, not because of some trick, Because time, actual physical time, the time between events, is not the same for everyone. It depends on how fast you are moving relative to me. Let me give you a concrete picture. Imagine a very simple clock. It is just two mirrors facing each other, with a pulse of light bouncing back and forth between them. Every time the light hits a mirror, that is one tick. On the train, the light goes straight up and down between the mirrors. Very simple, but from my perspective, standing on the ground, the train is moving. The light still has to go from the bottom mirror to the top mirror, but the top mirror has moved sideways while the light was in transit. The light has to travel a diagonal path. A diagonal path is longer than a vertical path. The light still goes at c, the same speed for both of us, so it takes longer to complete one tick. The clock on the train, seen from the ground, ticks slower. And this is not just one particular type of clock. It is all clocks. Mechanical clocks, atomic clocks, biological clocks, the aging of cells, the decay of radioactive atoms. Everything that measures time runs slower for the moving observer, because it is not the clocks that are slow. It is time itself. This is called time dilation, and it is not a metaphor. It is not an approximation. It is measured fact. We have clocks precise enough to detect it. Put an atomic clock on an airplane, fly it around the world, bring it back, compare it to an identical clock that stayed on the ground, and the traveling clock is behind, not by much, a few hundred nanoseconds, but by exactly the amount Einstein's equations predict. The global positioning system that helps people navigate relies on satellites carrying atomic clocks in orbit. Those clocks tick at a different rate than clocks on the ground, partly because of their speed, partly because of gravity, which is another story. If the engineers did not correct for relativistic time dilation, the positions the system reports would drift by several miles per day. Every time someone uses a satellite to figure out where they are relying on Einstein being right about time. Let that settle for a moment. Time is not universal. Your seconds and my seconds are not the same seconds if we are moving relative to each other. But it does not stop there. If time changes, space has to change too. This is not optional. It is forced on you by the same logic. When I watch that train go by at half the speed of light, I measure the train to be shorter than the person on the train measures it. The train, in my frame, is physically contracted along the direction of motion. This is called length contraction. The faster the train goes, the shorter it gets in my measurement. And I want to be very careful here. This is not an illusion. It is not like perspective, where things look smaller when they are far away. If I could somehow arrange a measurement, a real physical measurement of the length of that train as it passes, I would get a shorter number than the person riding on it. Space itself is being squeezed. People struggle with this, and I understand why. You want to ask, but who is right? Is the train really shorter or not? And the answer is there is no really. Both measurements are equally valid. Length is not a property of the train alone. It is a property of the train and the observer together, much like direction. North is not a property of the compass needle alone. It depends on where you happen to be standing on the earth. This is the revolution Einstein brought. Not just new equations, though the equations are beautiful. A new understanding of what measurement means, what objectivity means, what really means when you strip away assumptions you did not know you were making. So already we have lost two things we thought were absolute. Time is not universal. Length is not universal. Both depend on relative motion. Now let us push this further. What happens if we go back to our original question about adding speeds, but now we do it correctly? You are on a spaceship moving at 90% of the speed of light. You fire a missile forward at 90% of the speed of light relative to you. Common sense says 90 plus 90 is 180% of the speed of light. The missile should be going faster than light. But common sense is wrong because common sense was built on everyday experience, where things move at negligible fractions of the speed of light. When you add velocities correctly, using Einstein's formula, you do not get 180%. You get something like 99.4% of the speed of light. The formula is not complicated. If one thing moves at speed v and something on top of it moves at speed w, the combined speed is not v plus w. It is v plus w divided by 1 plus v times w over c squared, where c is the speed of light. At low speeds, v times w over c squared is practically zero, so the formula reduces to plain old v plus w. Galileo was right for slow things, but at high speeds that extra term in the denominator grows, and it prevents the total from ever reaching c. You can try any combination you like. 90% plus 90%, 99% plus 99%, 99.99% plus 99.99%, you will never reach 100%. You will always get something just below the speed of light. It is like a mathematical ceiling that you can approach but never touch. But I want you to ask a deeper question. Why? Why does the universe have this structure? Is the speed of light just some arbitrary speed limit, like a highway sign? Is there a cosmic policeman handing out tickets? No. It is much deeper than that. And to see it, you have to let go of one more thing you believe about reality. You think of the world as 3 dimensions of space and 1 dimension of time. Up, down, left, right, forward, backward, and time moving along separately, like a metronome ticking in the background. Space is the stage. Time is the clock. They have nothing to do with each other. That picture is wrong. In 1908, Hermann Minkowski, who had actually been one of Einstein's mathematics professors, stood up at a conference and said something extraordinary. He said, "From now on, space by itself and time by itself are doomed to fade into mere shadows. Only a kind of union of the two will preserve an independent reality." What he meant is this: space and time are not separate things. They are 2 aspects of a single entity called spacetime. And just like you cannot understand the shadow of an object without knowing the object itself, you cannot understand space or time separately without understanding the spacetime they both belong to. Let me try to give you a feeling for what this means. Think about directions. I am standing facing north. I say that wall is 5 feet to my left. You are standing facing east. You say that same wall is 5 feet in front of you. We disagree about the direction, but we agree about the distance. The wall is 5 feet away. Our measurement of left versus front depends on which way we happen to be oriented, but the actual distance does not. Something very similar happens in space-time, but instead of different orientations in space, we have different states of motion. When you move relative to me, it is like we are facing different directions in space-time. You slice space-time differently. Your space is tilted relative to my space. Your time is tilted relative to my time. That is why we disagree about lengths and durations. But there is something we always agree on, a kind of space-time distance that does not change no matter who measures it. It is called the space-time interval, and here is the remarkable thing about it. When you compute this interval, space and time do not contribute the same way. In ordinary space, if you go 5 feet forward and 3 feet to the side, the total distance comes from adding the squares, 5 squared plus 3 squared. But in space-time, space and time have opposite signs. The interval is the time part squared minus the space part squared, or the other way around depending on your convention. The point is that minus sign, space and time are not the same kind of thing. They are woven together, but they pull in opposite directions, and that minus sign is where the speed limit comes from. Let me explain this more carefully because it is the key to everything. In ordinary space, distances work the way Pythagoras told us. If you walk 5 feet east and 3 feet north, your straight line distance from where you started is the square root of 5 squared plus 3 squared. Both directions contribute positively. You can go as far as you like in any direction. There is no max